Okay, thank you very much. It is my great pleasure to come to this wonderful conference, and I'd like to thank the organizers for inviting me. So today I'm going to talk about some very recent results from my group on mechanochemical active solids and their nonlinear dynamics. And this is an example of chaos, I think, as David just asked. So I'll have a very brief introduction. I think we all know that active solids is a very active field, and in the past several years, many really cool experiments and theories have been put forward. And if you think about the experimental platforms, they are in general two big classes. In one class, you have these metamaterials, robotics-based active solids, and like Gustav just talked about. And in another class, you have biological active solids where there is intrinsic dynamics from the biological processes. So these two types of systems have their pros and cons. In the first case, the system is controllable. You know exactly what is happening in the system, but on another hand, it needs careful design and engineering. And for the other type, the system is self-assembled. It is scalable in the sense that you can have an active solid with a very large number of degrees of freedom, and then you can observe nice collective dynamics. But at the same time, the system is very complex, and there is a lot going on. So one thing we have been thinking about is, can we find experimental systems that are somewhere in the middle, which are both simple and scalable at the same time? We are looking for systems where you have materials intrinsic driving instead of engineered agents. And we are also interested in seeing non-living statistical mechanics instead of biology so that we can write simple theories. And besides these 2 points, we are also interested in a somewhat new regime of active solids where we have fast elastodynamics. So these considerations led us to consider this type of system called mechanochemical solids. So I realized maybe mechanochemistry is not something everybody is familiar with. I included some videos to give you an intuitive sense. So mechanochemistry refers to chemical reactions that are sensitive to mechanics, sensitive to stress and strain. And these solids often have these so-called mechanophore, which are functional groups that can undergo mechanically induced covalent transformations. So in the first video, you see there's a little piece of gel where when you hammer it, it immediately changes the color. So the mechanical stress causes some really fast chemical reaction. In the second case, similarly, there's a balloon, and when they blow it up, it changes the color because the mechanical stress caused the chemical reaction. And these are from my collaborator Steve Craig's group. And here is a third example where mechanics cause chemistry in a reversible way. So when you stretch this piece of gel, it causes luminescence, and it goes back on and off in a reversible way. So in all of these examples, we see mechanical stress causes chemistry, and it happens really fast. On the other hand, it is also known that chemistry can cause mechanics. Some chemical reactions can cause active stress. This is an example of a busy reaction gel, where people see that the chemical oscillation causes the swelling state of the gel change, and that leads to active stress. So what we have been thinking about is, can we have both of these two effects in the same material? So we can have mechanics cause chemistry, and chemistry come back to cause mechanics, and we can have an active feedback loop. So this kind of active feedback loop is probably plenty in biological systems. However, in a non-living system where we can engineer things, we're still looking for that. And maybe someone in the audience can tell me examples. I will be very happy to hear about that. So basically, we're thinking about this system because of potential advantages that it's a solid state system, so it's scalable, and we can describe things with simple statistical mechanics, and we can have fast dynamics. So what do I mean by fast dynamics? Here, if you look at this video, it has been sped up a lot because this is a reaction diffusion system. Diffusion is really slow, so the time period for the chemical oscillation takes a very long time, and it makes it hard to couple it with elasticity in a meaningful way. However, if we can replace reaction diffusion by reaction elasticity, we can have really fast reactions. And it can couple with the elasticity timescale and give you potentially interesting phenomena. So this leads us to the topic I would like to discuss today, which is on one ongoing project on nonlinear dynamics of active solids through non-reciprocal mechanochemical feedback. So the work is done in collaboration with Siddhartha Saka, who was a postdoc in my group and now work at MBI Dresden, and my current postdoc, Bisu Ash, my undergraduate student, Yueyang Wu, and my new colleague, Suraj Shankar, who I think most of you know, and also my collaborator, Nick Beckler from UCSD. He is a mechanical engineer, work with stimuli-responsive materials. So in the talk, I'm going to first give you a brief review of statistical mechanics of mechanochemical reactions, and then I'll talk about the nonlinear dynamics of a simple model that we came up with describing these systems from a zero-dimensional harmonic oscillator with a chemical reaction to a one-dimensional solid. Basically, what we try to do here is to write some fundamental wave equation type of theories, and the system has mechanochemical coupling, and we want to see what kind of nonlinear dynamics this coupling leads to. Okay. So let me first spend a few minutes on the basic statistical mechanics of chemical reactions. Maybe some of you are already familiar with it. I'm just going through the basic steps, right? So imagine a simple chemical reaction, for example, M of A molecules and N of B molecules going into O of C molecules. We know in statistical mechanics, chemical reaction is considered as transitions between microscopic states. So the language we need to use to describe them are forward and backward reaction rates. So in the same system, you can have the reaction go from this way or this way. And you can draw a free energy, molecular level free energy versus molecular reaction coordinate that describe the initial state, final state, and there is usually a transition state that represent a barrier of the reaction. Okay? So the forward rate is proportional to the concentration of the initial molecules, so A to the mth power, concentration of B to the nth power, because you need this many molecules in the same volume element for the reaction to happen. At the same time, it is also proportional to a reaction coefficient, and you can similarly write it for the backwards rate. These reaction coefficients are determined by the so-called Arrhenius law. Basically, you write a Boltzmann factor of how likely for the system to climb over this barrier. Okay? And at the system statistical mechanics level, you can have these rates. So when the system is at chemical equilibrium, which means forward and backward rate balance with one another, you have these two rates equal, and you can derive a simple relation between the concentration of the molecules and the difference of the initial and the final state free energies. Okay? And this, with a few more lines of math, you can show that it is actually equivalent to writing M shares of chemical potential of A plus N shares of chemical potential of B is equal to the chemical potential of the final state. So the system is at equilibrium. You move forward a little bit, backward a little bit, the variation of the free energy is zero. And this is, again, standard textbook material, but it's actually pretty interesting, right? So remember, when we learn basic chemical reactions in high school, we learned that they are exothermic reactions and endothermic reactions, which means reactions that let out heat or takes heat. At the time, I was really confused why endothermic reactions ever happen, right? So it means that the initial state is lower energy, final state is higher energy. Why do you have such reactions? And this kind of formulation explains it because the chemical potential has two parts, one from the concentration, the other from the molecular free energy. It is when you have a lot of A and B molecules together, the effect tells you that the system wants to react and go to a high energy state. Okay. So this is chemical reactions without any mechanics, right? Now we want to add mechanical stress to this picture. It's not going to change these basic equations. The only thing that will change are these potentials, or the free energy of the molecular states. When you have a mechanical stress, it could stretch a polymer or change the shape configuration of some kind of molecule. That changes the initial, final, and the transition state. And for mechanochemical solids, often what happens is that it lowers the barrier and make the chemical reaction happen faster. Okay, so the only thing changes is the F plus and the minus. And we can do a simple expansion around the stress-free state. I will not go into too much detail. So with these basic equations at hand, we can now write coupled differential equations to describe the nonlinear dynamics of these systems. Firstly, we introduce a chemical reaction variable, which is just the extent of the reaction in the whole system. So it's a variable between 0 and 1. 0 means the whole system is here on all A and B molecules, no C molecule. That's just an example, right? And 1 means that everything that can react already reacted. And if it's a number in between, that means part of the system is here, part of the system is here. Okay? And it is different from this coordinate here. This coordinate is the chemical reaction coordinate, and chi is the system level statistics. So the time derivative of the chemical reaction extent is the forward rate minus the backward rate. And this is where the mechanics comes in, because these rates now depend on the state of the stress. And similarly, we can write down the time derivative of the mechanical degrees of freedom, which is the displacement field in the solid. And these terms are just the normal wave equation terms of a viscoelastic solid. So here I would like to also join the discussion of viscoelasticity versus limit cycles we had in this morning, right? So if you just have this part of the equation, this is inertia, this is elastic restoring force, and this is the viscosity term. The system has oscillations, but it does not have limit cycles. Because you have dissipation, the energy will eventually go away, and you will go to fixed points where everything stops. In order to have limit cycles, there needs to be some active mechanism that balances the dissipation, and that is what we're trying to show here with mechanochemical coupling. There is an active process that burns the chemical field that keeps the viscoelastic solid oscillating. Okay? So here, the chemistry variable enters the mechanical equation in this particular form. So what does it mean, right? So you can think of a simple illustration like this. Say I have a polymer-like material like this, where it has some mechanical force, where when I stretch it, some chemical reactions happen. And when the chemical reactions happen, some molecules come out, just hypothetically change the state and causes active stress. So either it makes the system expand more or makes it want to contract, and there's a feedback loop between chemistry and mechanics. That's what we are trying to write in these coupled equations. This term looks like this because you can imagine there is a preferred mechanical state before the reaction. Say, for example, the volume is smaller. And there is a preferred mechanical state after the reaction, say it causes it to expand. And for a local volume, you average over the two terms and you get a term like this. And this kind of illustration may remind you of something you have learned in introductory courses, which is an internal combustion engine, right? So in an internal combustion engine, when you compress the fluid in the engine, it causes a fast chemical reaction, and that will cause fast expansion and push back on the piston. And the piston has a lot of inertia, so it keeps going and you have a limit cycle. So here you have complicated machineries to keep the system going. And what we're interested in this problem is to see, can we have a solid state system with this kind of balance between chemical energy and mechanical dissipation and have active process going on. Okay, so that's a basic setup, and now let's see what exactly does this equation look like and how do we write down the differential equations when they are coupled. So let's first look at the simple case when the system is in chemical equilibrium in the stress-free state. We know that in chemical equilibrium, you have balanced forward and backward rate, so it's just one number, and you can pull out the coefficient, you get the time derivative of the chemical reaction equal to this coefficient times the mechanical variable. And now you compare these two terms, you can see that in this case, when the system is near equilibrium, the mechanics and the chemistry are reciprocal. as you would expect from Onsager relations. So the way chemical reactions affect the mechanical equation and the way mechanical variable enters the chemistry equation has the same coefficients. And this is a manifestation of reciprocity. In contrast, if you start with a non-equilibrium system, where the chemical reaction did not happen all the way to equilibrium. For example, you have a high barrier that needs to be activated by some mechanical stress. In this case, the forward and the backward rate in the stress-free state is unequal. And you cannot do the simple simplification. You have to keep the terms. And you will see that there will, in the chemical dynamics equation, there will be a term that comes from the mechanical stress, where I have the elastic stress part and the viscosity stress part. Now this is non-reciprocal because they are controlled by different coefficients. And again, now in this case, if you derive the chemical potential of the different species of molecules, you can see that you no longer satisfy this equation. And in essence, here, when you have self-sustained oscillations, it is burning the chemical field to output mechanical work. Okay, so now with these equations, we can arrive at a slightly simplified version by just doing leading order expansion. And this is a coupled equation of a mechanical degree of freedom and a chemical degree of freedom. So if you did not completely understand the earlier part of the statistical mechanics of chemical reactions, it is actually okay to forget about all of those and just start from these equations, where this equation here, the first part is just viscoelasticity, right? So inertia, elasticity, viscosity, and we add a new term, which is the influence of chemistry on mechanics. So chi is the extent of chemical reaction. It gives you an active stress, and the derivative of that active stress is the force that enters this equation, okay? Second equation is chemical reaction. This term is diffusion, and this term is reaction. So we write it in a way that you have a double well potential, and the first order derivative is like this. That is a bistable chemical reaction. Just for example, you can put any potential here, okay? And this term is the effect of mechanics on chemistry, where a strain can accelerate or deaccelerate the chemical reaction. And similarly, the strain rate can also change the reaction. So in fact, this is where we started with when we started to work on this project. We just thought like phenomenologically, can we write wave equations with chemical reactions? And we wrote something like this. And we found that interestingly, by changing the sign of this parameter, which controls reciprocity, you see completely different phenomena. And then in order to justify why the equations look like this, we went back to do all the statistical mechanics to understand what exactly this is. And now we understand that it is really the equilibrium of the chemical reaction. Okay, so anyway, we show that when this is a positive number and we don't have the strain rate dependence, you can actually write the whole thing as if it comes from a free energy functional. So the whole thing is relaxational dynamics. And then you can break this relaxational dynamics, for example, by changing the sign of Kavli, which make the strain chemistry interaction to become non-reciprocal, or you can keep it positive but introduce a strain rate dependence that also makes the system active. So these equations look somewhat complicated, so we non-dimensionalize the equation. At the same time, we see that there are three timescales in the problem. The first timescale is the elasticity timescale. So this is the velocity of the elastic waves. When you take the system size divided by the velocity, it is the timescale for an elastic wave to travel from one end to the other end of the system. This is the diffusion timescale, which using the diffusion coefficient, it is the timescale for the molecules of the reaction to diffuse from one end to the other end. And this is the chemical reaction timescale. When you have a driving force versus the dissipation, the damping coefficient of the chemical reactions, it describes how fast the reaction happens. And we are interested in the regime when the chemistry and the elasticity are comparable, and we can have a nonlinear coupling system between elasticity and chemical reactions, and they are together much faster than diffusion, because diffusion is typically slow.
Sorry, I just have a quick question.
Yes.
The reciprocal limit presumably would actually impose a value on Xi, not just on its sign, right? Because strictly speaking, if it comes from an energy function, those two coefficients will actually have to agree, not only in sign, but in actual value. But
yeah.
This is sort of, I guess, qualitatively reciprocal and non-reciprocal in that sense.
Yeah, that's a good question. I think we also thought about it a lot, because if you change the value here but keep the sign, you can actually absorb it to this coefficient. And basically it means that you can somehow change the time scale to absorb that. Technically, I think it somehow violates the reciprocal relation, but dynamically you see basically the same phenomena. Okay. Any other questions before I move on? Yes?
Seems to me that you could in some cases eliminate your chemical field by integrating it out and create some of those active elasticity that you see this morning. To some extent, for example, in my talk, I have the C field, which is a chemical reaction essentially happening. You integrate the C out, you modify how they interact with the particles. And I'm wondering if you wrote down a U that is less driven in terms of tensor structure, right? So that you have gradient displacement field. You could pick up, for example, correction to the moduli. They come from integrating out that field, because after all, everything that is active is some other field, whether it's chemistry or hydrodynamics, that you integrate out and allows you to. Have you tried?
So I think in the beginning we tried to do that. So instead of a chemical variable, we just have some kind of internal variable, right, that has a field that you can burn. So we did not do much of that, but I totally agree. It is possible to write some kind of unified dynamical equations for all kinds of different active elements. Yeah, maybe it's worth doing that. Yeah, thank you.
In fact, to some extent, your call for polar elastic media indicate that by showing that the masses can have all elasticity once you include the fluid in and out.
Yes, that's right. Yeah. Okay, any other? Okay, so we then take these equations and did some simulation in a one-dimensional system where here I show you some examples where these are plots of the displacement field as a function of space and time. You can see that in some cases, the system reached some steady state. In this case, it's just a simple steady state. The system is homogeneous. In this case, because of periodic boundary conditions, part of the system contracted, the other part expanded because I have two fixed points, right? I have an interface in between. And in the middle, the system arrives at different types of limit cycles. And on the right, as you change the parameter, there are also regimes where you see interesting period doubling and chaos. So there is a rich phase diagram in these equations. So these are partial differential equations that are somewhat difficult to analyze. So really to understand the essence of the problem, we started by looking at a zero-dimensional problem, which is much simpler. We just consider a harmonic oscillator which represents maybe one mode in the elastic solid, okay? And then we couple it to a chemical bistable reaction. So simply when you look at this equation, you realize that what it means is that the tethering end of the harmonic oscillator is in a double well potential. It's actually really simple, right? So this part, the two first equations without this box is just a damped harmonic oscillator. We add a chemical reaction here to say that as the reaction goes, it gives a force that pulls the other end of the harmonic oscillator. And this equation is the chemical reaction, which has the influence of the displacement and the velocity. Okay, so we start from such a simple system. And again, you see that in the reciprocal case, when Xi is positive and I don't have this B term, the whole thing can come from a free energy, which I have a mechanics harmonic potential and a bistable chemical potential and a coupling term. So the coupling is actually really simple, right? So if you plot the free energy as a function of your chemical parameter. When you don't have mechanical signal, it has a symmetric double well potential. And when you pull the harmonic oscillator left and right, you tilt this potential in different ways. So in this case, we start from a reciprocal passive system, and we will just observe relaxational dynamics around the fixed points. In contrast, now if I change the parameters, I either make the Kc into a negative number, which means there is positive feedback between the mechanics and the chemistry, or I can make this be non-zero. So in both cases, I see that the system has 3 fixed points. One is a 0, 0, and then you have 2 fixed points, which means basically you can think of them as having 2 double well potentials, either this one lower or this one lower, but both the mechanical or the chemical coordinate will need to adjust to the fixed point values. So then we did some really simple numerical simulations and find phase diagrams basically like this. So this is the first case when I have non-reciprocity in the U and chi coupling, but have no strain rate dependent. So this is a phase diagram in terms of mechanical damping coefficient, which is a viscoelastic coefficient here, and the non-reciprocity. So when this Kc is 0, above 0, it's a reciprocal system, and under that, I have a critical point where the system changes from 3 fixed points to 1 fixed point. However, for this whole area, because the damping is so strong, even though you have non-reciprocal reactions, the system will always converge to some fixed point. In this case, there's actually always a fixed point in the middle that it remains the trivial solution of 0, 0. It is only when either non-reciprocity is strong enough or the damping is reduced, I enter this phase of limit cycle where, again, burning chemical field give you sustained oscillations. Okay, but you need to tune the parameter right so that it has enough energy to sustain, to overcome the damping. And the other case is to keep this parameter positive and introduce a strain rate dependence. Basically, I kick the reaction according to the velocity, always in the right way so that it can keep going. Right. So here I also have 3 fixed points, but I get a phase diagram like this. So here I take B to be a positive value, and then again the 2 parameters are mechanical damping and non-reciprocity. So here is actually Kc is positive number, right? But for consistency, we still use these parameters to draw the phase diagram. So similarly, yeah. Yes, that you can see by looking at this matrix here. Yeah. So the stability of the fixed point, so this crossing line, you can completely get from the bifurcation analysis here. But something in the middle, we have to find it numerically because it's like fully nonlinear.
Is there an exceptional point? What is the mechanism?
Mechanism for which one?
What kind of bifurcation is it?
Yeah, I have a figure. Yeah, okay. So here, in this case, the fixed point is actually around 2 of the fixed point on the end that in the corresponding to the 1D model cause inhomogeneous system. And when you reduce the mechanical damping, it gives you a limit cycle around one of these fixed points. When you have even lower damping, you have a large limit cycle that includes all of these points. But in the middle, there is a range where the system kind of hesitated between limit cycle here or limit cycle here, and it runs into chaos. And I think answering your question, the bifurcation, when we tune the parameter down along this line, you can see the bifurcation happening in this way that you get a period doubling and in the end a full chaos. Okay. So this is like a simple limit that can help us to draw the correspondence and explain the observation in the one-dimensional case, which I think I'm running out of time, so I will not go into the details here. So I want to wrap up. So here we look at mechanochemical coupling, where we use chemical field to obtain fast elastodynamics, and potentially they are interesting nonlinear dynamical systems. And we reach scalable self-sustained active solids. And we're looking for experimental systems to realize these interesting observations. Thank you for your attention.
Thank you very much. Okay, let's start on the left.
Thank you very much. Thank you very much. Very interesting. So at the beginning, I don't know whether you found a mechanical system that works as the key example for your case. But many of the things that you said at the beginning, there is a class of material called liquid crystal elastomers that are photoactive, and they have molecules that respond to light with a configurational change. And that looks very much like your picture. Instead, the second part where you do the interaction, you do the coupling, so where the reaction coordinate is coupled linearly with the displacement, that's, okay, doesn't look familiar to me. So, okay, this is both a comment in the sense that that field is right for you to get a lot of things, but also a question about the coupling that you chose.
Right, so the coupling here, are you referring to the variable chi?
Yes.
Yeah, that is not a reaction coordinate. So I drew the double well potential for the reaction coordinate, but the parameter chi is the extent of chemical reaction at a statistical level. So the reaction coordinate, to my understanding, refers to the molecular configuration. Yeah, so I think those equations we kind of borrowed from earlier statistical mechanical theories of single molecule mechanochemical reactions. When there is a force that pulls a chemical apart, it changes the reaction rate of forward and backward. We extend that to stress in a solid, basically. Yeah.
No, just to elaborate, I just meant that the first part, there are systems that behave exactly like you want. They can be fast. Yeah. They don't need 250 times acceleration, and they use this mechanism that there is a polymer with a photochemically active molecule. And so I said that is definitely a field ripe for your attention, but the coupling between whatever chi is, so the coupling of chi with a linear displacement, I don't think that field works like that, but that's my...
I see, okay. Yeah, the first part, I mean, if I understand you right, you're referring to mechanics cost chemistry, right? That part, I think there are many examples, like you said, but how chemistry generates active stress and come back to mechanics, whether it's described by that, that's not clear, right?
But are you concerned by the fact that you couple to displacement instead of strain, or are you concerned by... Is it the linearity of the coupling that concerns you, or the general...
In the system, I know you have to model light propagation inside the system, so the system becomes opaque as the transformation takes place, and so the coupling is complex. It's very complicated. But anyway, it's very interesting.
In some sense, what we are trying to write is a phenomenological theory that captures a leading order effect. Right? The actual thing can be much more complicated.
Okay, so let's, no, to the right now.
Okay. So I have a question that's related to what Vincenzo asked. So can you go back to this, so you have this from, I think you have fixed point and then you got, right. So my question is, you have this 3 fixed points that, and then it converted to a limit cycle, right?
Yeah.
So my question is, in that red regime, are there 2 limit cycles that are stable, or there only?
Yeah, there is a limit cycle here and another one here.
And so because that excites us, because me and Vincenzo and others have written a paper that tells that if you, I think there, starting from 2 limit cycles, I think in conversion to 1, which is very much similar to the non-reciprocal phase transition, where if you look at the not only the Dafinov exponents, but Dafinov vectors, that's where the 2 Dafinov vectors coalesce. And so it's very similar.
I see what you mean now. Okay.
Yeah, so because there's one-way coupling between this, how to say it? I don't know, like direction of the fluctuation along the 2 fixed point axis versus the limit cycle, I mean, the 0 Dafinov exponents. And those, I mean, what we showed is that they coalesce when you have 2 limit cycles.
Yeah, exactly. That is this point, the bifurcation where the 2 orbits collides and have period doubling. Yeah.
Okay, yeah, thank you.
Yeah, I see. Thank you.
No, Dave, we have plenty of questions on the line. Sorry. So next to the left, maybe at the end, so please.
Thanks, that was a very nice talk. As an experimentalist, I was wondering that like a lot of systems that are likely to have mechanochemical interactions, most of them are well described by overdamped dynamics.
Yeah.
So how important is inertia in your models?
So in my case, it is very important, right? I would not have these if I don't have the inertial term.
But I mean, in principle, what would you need if you don't, let's say, like if you wanted to...
So I'm really not an expert on nonlinear dynamics, but I think there are some theorem also that you need 3 coupled fields in order to have chaos, right? So here it is really, we're making use of inertia. So you have both U and V. If it's overdamped, then you need to have coupled it to something else.
Yes, but you could have multiple components of the displacement field in addition to a...
Oh yeah, that could work too, yeah. If you have some kind of internal variable that cares about moving this way or that way, that's possible too, yes.
Thanks.
Yeah.
Okay, to the right.
Yeah, I guess it's also a question related to dynamical systems. I don't know very much, but it seems to be somehow related to relaxation oscillators, plus an extra degree of freedom here in your dynamical system. So I guess my question is, do you know what the relation between, like, it seems like you're adding an extra degree of freedom to your relaxation oscillator, I guess, and my question is, do you agree, and do you think there's a relationship between those two?
Between what and what?
Well, a relaxation oscillator is maybe, like you have an oscillator, like you have a field that takes you to one minimum, then you had your picture with your energy minima, right? So
this picture,
this one,
right?
yes, and I guess the question is this picture or intuition of the mechanism in a relaxation oscillator relevant, and what would your extra inertia related term do to that?
I see, yeah, I'm not familiar with exactly the relaxational oscillator, but here, if it's a passive system only having bistability, I would not have the complex dynamics, right? There has to be something else that kick it in a direction that is opposite to the relaxational dynamics. I don't know if that's what you're...
But usually in a relaxation oscillator, that's a negative resistance, for instance, right? That does that for you.
The relaxational...
Yeah, usually in a relaxation oscillator, like neon light, it's a negative resistance that does this for you.
Oh, okay. So that I need to think more. So you have some other internal degrees of freedom that when you integrate it out, it seems like it gives you a negative coefficient.
The way I view it is that here you have your bistable minimum, and you can oscillate around the left minimum or the right minimum, or you can encircle both, I guess. Usually in a relaxation oscillator, you go from one to the other, right, like this.
Yeah.
Yeah.
I see. Okay.
But again, that's a half-baked thought.
Yeah, thank you.
Simka.
Yeah, I think we have, there is a biological example of the sort of mechanism you're talking, which is in tissues where you have actomyosin cortex, which is stress sensitive. So you get things like catch bonds where the reactions are sensitive to this thing. And in fact, you can write down overdamped equations, which are sort of cousins to what you have, and get some of the same phenomenology. So it does have, mostly it has just fixed points. Sometimes you can get limit cycles. You usually can't get chaos for the same reason that you get, but you can get something like a motor in steady state. So there are, I think there is a whole class of these materials, and so there, yeah, this is a bit broader, yeah. Thanks,
Yeah, I think that's a good point. I think a similar type of dynamics you can write for biological systems, right, and do this kind of analysis. I think I still need to learn more about how much theory has been done for the type of system you referred to.
I think everybody is just starting,
okay.
So it's, yeah.
But it's true that in this case, the elastic part is overdamped, right?
Right.
So there must be some additional thing, because here if you overdamp the elasticity, but then Christina is going to react, but so here if you overdamp the elasticity, nothing takes place. So Christina, please.
So indeed, these kind of models, these kind of models have been actually used to describe, for instance, sustained oscillations in, say, cytoskeleton or living tissue, where your chi would be a native stress, where first of all the dynamics is overdamped, and then indeed you need three equations. So your chi would be a native stress, which has its own dynamics, and in turn couples to say the concentration of phosphorylated myosin, so activated myosin. And then you get sustained oscillations, and you get very much the same type of behavior. Yeah. And indeed, people have discussed quite a bit the relative roles of coupling to strain versus strain rate, which can give you different things. So again, very similar equations with no inertia, just damping, and but generally you need the third equation, as you were saying. So since people raised this question, I just want to make that.
Yeah, thank you. I think that sounds like really related. Yeah. Yeah.
Please.
Great topic, because I want to piggyback on that from the microscopic perspective, because a great example of a chemomechanical reaction is indeed actomycin or also microtubule kinesin. They both rely on the power stroke, which a good reaction coordinate is beginning of stroke to the end of stroke. And that couples, again, to stress or strain, depending on how you like to see it. So it would be a great thing to continue on with that.
Yeah, that's a good suggestion. Yeah, thank you.
On the right again?
Yes, thank you for the talk. So again, connecting to the work that was done before on actomyosin for cytoskeletal networks, in some of these models there is also advection and concentration. Can you hear me? Or?
I can hear it.
Okay.
Trying to follow. Yeah.
In some earlier models, there were also advection and coupling with the chemical that comes from concentration due to compression or expansion of the material. And here, do you have such couplings, or is the chemical following the material, or no?
I think we wrote that in our paper, or paper 2B. So, but in the simple analysis I described here, we did not include the advection term. It should be there. So I think here is just like the first order simple analysis.
Maybe you can create a Xi, one value of Xi just from the compression, no?
Create a
Xi, the Xi term.
A Xi term.
From the strain, if you have a positive strain, you concentrate the chemical. That's that.
That may be possible. Yeah, we have not considered that yet.
Okay.
Yeah, thank you.
Okay, and so the last question is for Dave. It's your turn. No more questions? Oh. Okay, so I think we can conclude here perfectly on time this morning session. I should thank all the speakers who didn't ask me to be severe. They made it spontaneously. Thank you for the self-organization. And so we meet again after lunch. Thank you very much.
Thank you.